Good afternoon. Welcome to today's SCA webinar with Dr. Rajan Shochki on why and how gas lift is different from Gulf of Mexico to Permian Basin. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I'm going to launch the polling questions. And the first question is, what is your primary discipline? So we're starting to get some responses. Good blend between petroleum engineers, geoscientists, facility engineers, and other. Votes are still coming in, but largely petroleum engineers and geoscientists. So I'm going to close and share those results. And then our next question is, how many years of full-time experience do you have in the upstream oil and gas industry? Again, we're just taking the demographics of the audience. Your answers are coming in now. Quite a few of you have over 30 years of experience. But looks like it's a pretty good distribution between all the categories. Most of you have voted, so I'll go ahead and close and share the results. We have some in every category except for less than 1 year. So everyone in our audience has experience with a good distribution. So thank you for that. So before I introduce Dr. Shoshki, I'd like to remind the audience that you are muted, but you can ask questions during the presentation using the GoToWebinar question feature. And this is the webinar on why and how gas lift is different from Gulf of Mexico to Permian. And our speaker today is Dr. Rajan Shochki. He is an expert in artificial lift. He is the production optimizer for Accutent Solutions. He has more than 30 years experience working in a variety of roles, and he's worked in global projects around the world. He's been quite active in the Society of Petroleum Engineers. He holds 2 patents, and he's been involved in a number of forums. He's served as SP Distinguished Lecturer twice, and he teaches a number of courses for SCA. You can see several of the courses listed there. The course he is teaching that's coming up in March is entitled Producing Unconventional with Gas Lift from Annular to Pagel to Plunger Lift and in Between. So that course is being offered March 4 through 6 in SCA's Houston Training Center. There's also a class that Dr. Shochi teaches that's in October on data analytics workflows for artificial lift, production, and facility engineers. SCA also has a number of free webinars on the calendar coming up. On February 6th, we have Dr. Ben Clark and Dr. Amalia Oliveira Riley speaking on powering purpose, fueling team performance in the energy sector. And Dr. Amalia Oliveira Riley leads SCA's business advisory services. In March, we have Brad Prather speaking on deep water systems classification and sediment partitioning. And Dr. Shoshi is back in June with production data needs TLC2. We have some live online classes that are coming up in March with Dr. John Lee, production forecasting for low perm reservoirs, and then PRMS and SEC reserves and resource regulations. And of course, SCA training classes, in addition to be offering in a public venue in our training center in Houston, can also come to your office if you would like to have them in-house. So choose SCA not only for training, but for all your consulting needs, for direct hire staffing services, and for projects and studies. And so I'm going to pass the presentation rights to Dr. Shoshi, and you should be able to share your slides.
Okay. All right. So you should be able to see my screen.
Looks good.
Okay. All right. Good afternoon. Thank you, Susan, for this opportunity and the introduction. Good afternoon, good evening, and good morning. I understand we have quite a wide variety of audiences here, and I appreciate very much all of you deciding to share your time. It is possible that some of you may not be working in either of this area, Gulf of Mexico or Permian Basin. So I applaud your desire to learn more. However, I do assure you that you will have some learnings here or some takeaways that you'll be able to apply in whichever asset, wherever you are working. Now, the webinar format would not allow us to go into all the details, and we'll be touching things at somewhat higher level. However, in the class version of this activity, we'll have quite a few hands-on exercises, including some of the data-driven digital oil field related exercises also. And as Susan was mentioning, this class can be customized and it can be brought to your facility also. I have customized it for a few clients using their own data. So coming back to the subject matter, first thing is before we start talking about gas lift, we have to understand that oil and gas life cycles, they follow a distinct pattern. On the left side, we are looking at the conventional reservoir. On the right side, we are looking at unconventional reservoir. There'll be some build-up time, there'll be some naturally flowing period, and then there'll be decline. In unconventional, the decline can be very steep. Regardless of whether it's a conventional or unconventional reservoir, you require some form of artificial lift. And the focus of this talk is on the gas lift. We have a sampling of the conventional reservoir when we talk about Gulf of Mexico. And then we talk about unconventional production primarily when we talk about Permian, even though Permian traditionally has conventional production also. But for the purpose of today's discussion, we'll be focusing on the unconventional aspect just to make you aware of the different characteristics. So with that, when we look at the different types of artificial lift, there are 8 or 9 or even more, depending upon how you count. Just in the broad brush strokes, we can subdivide this lift method in terms of their capacity. On the right side here, when we look at the jet pump, ESP, and gas lift, they are higher volume lift methods typically. And on the left side are the plunger and foam lift, which are low volume methods. And in between, we have medium. So when I say low, high, and medium, we have to keep in mind, we are looking at about more than 800, 1,000 barrel type of, which will fall under the high. Upper end could be as high as 30 or 40,000 barrels per day of liquid. And lower end, we are typically talking about less than 50 barrels per day. Having said that, we have to keep in mind that gas lift could be high, but the configurations are possible whereby you can produce as low as less than 10 barrel per day. So just don't take away with the idea that gas lift can only be used in high volume liquid production. And the same applies for jet and ESP, though each of these lift method, they have their own application envelope. So your takeaway should be that gas lift is one of the higher volume and versatile lift method. When we talk in terms of what type of energy source this lift methods use, then gas lift falls into the same category as plunger and foam lift in that the primary energy source is a reservoir. And whereas in case of rod lift, piston, jet pump, PCP, or ESP, in short, whenever there is a pump in any of the lift methods name, meaning you are lowering some device inside the valve bore or inside the tubular if the production is coming from the tubular, which is energized from the surface, and that is what provides the necessary dynamic head for the fluids to come to the surface. With this, if we have to understand the importance of gas lift, with ESP, these are the two high volume lift methods. And here I have taken an example from ConocoPhillips, one of the keynote address in the Artificial Lift Research and Development Council. And what we are seeing here is that in terms of well counts, year by year, from 2013 through 2022, the gas lift count is steadily increasing, even though the plunger lift and rod pump, as well as the flowing well counts are substantially higher for this particular operator, ConocoPhillips. However, when we look in terms of the volume, in terms of equivalent barrels of oil per day, what we are looking at here is that for this particular operator at least, the gas lift volumes are consistently increasing, even though the number of wells are relatively less. And when we look at their distribution of different lift types in different assets, global assets, whether it's a Permian or Gulf Coast region, Canada, Alaska, Norway, or China, again, what we are seeing is that next to the rod lift, which is predominant in the Permian, but if you look into the gas lift, again, gas lift has a higher penetration not only in Permian, but also in the Gulf Coast region and in the other region also, particularly when you look at the Alaska. So this should tell you that for not only this operator, but other operators also, whether you talk about ExxonMobil or you talk about Occidental, Chevron, each of them have relatively higher share of production coming from the gas lift. So gas lift is important lift methods. And just to round out some of the basics, we see here that gas lift is nothing more than just the extension of the naturally flowing well. The difference when you compare to the naturally flowing well, in gas lifted well, we figure out some way of injecting produced gas or natural gas inside the flow stream so that the flow stream gets lightened, not only by the formation gas expanding, but also injection gas. So again, the motive force is coming from the reservoir, but this injected gas will lighten the column. And so the main equipment, if you will, in the gas lift, as far as the inside the valve bore are concerned, then they are what is called a mandrel, which holds the gas lift valve. And then the location of this mandrel and gas lift valve is important because the deeper you go, the longer column of the valve fluids get lightened. But again, these are all the discussions that are carried out in details with the hydraulics related calculations in the class setting. By the way, we are not going to talk about a whole lot of equations, at least in this presentation. I just brought this momentum balance to emphasize again the point that was made in the previous slide, that when you take the pressure gradient in the production stream, then there are three components: elevation, friction, and acceleration. Elevation being the major one as far as the vertical or deviated production profiles are concerned. And for elevation gradient, the most important is the mixture density. So as you inject gas, you are going to have lower and lower density, which will reduce the pressure losses associated with the elevation gradient, right? Now, this graphic is showing that as you keep on increasing the gas oil ratio, meaning you are injecting more and more gas, the gradient, pressure gradient profile keeps on shifting to the left, meaning the gradient is becoming lighter and lighter. meaning the bottom hole pressure is becoming lower and lower. As a production engineer, our goal is to reduce the bottom hole pressure. So then you say, okay, why don't we keep on increasing gas? But what happens after a while, like as is shown here, around like as you keep on reducing to 5,000, the gradient becomes lighter and lighter. But as you go further down, increase further, the gradient starts shifting to the right. And now what we are seeing is that the friction is overtaking, even though the density is decreasing, but the friction keeps on increasing. Anyway, so this is the basic of the gas lift operation. So your takeaway so far from two slides should be that, okay, the depth of injection is important, location of the injection is important, and the quantity of the gas is important. And that is how it has been in the gas lift. When we look at the applicability of the gas lift, it is applied across the board in any type of asset as long as you have sufficient quantity of gas available. Um, and lately in unconventional place and deep water place, gas lift is more and more preferred. And that is another takeaway for you from this short webinar. The main reason for gas lift popularity is that it can work with even limited well data. It allows a full wellbore access, especially when you have higher gas oil ratio than the pump type of artificial lift methods. They suffer because of the volumetric efficiency issues, whereas gas lift, it likes the more gas. So that is another reason. Gas lift is applicable for thermal wells also. Whenever you have variable production rates, gas lift doesn't have as many challenges like some of the pump systems because each pump device has its own operating envelope. So if you have to summarize this slide, you can say that the gas lift has one of the widest operating envelope, and that's why it is a preferred lift method in many, many scenarios. Okay. Typical design workflow, as I mentioned earlier, you're trying to determine what is the depth of injection, and what is the injection rate for a particular given injection depth. And then initially your wellbore may be full of completion fluid. And so you have to remove that completion fluid before the regular injection or the gas lift normal process can happen. So you have to figure out some of this, like what should be the location of this unloading uh, minerals. Also, you have to figure out what is the compression horsepower requirement for the field. Now, it is relatively a smaller exercise when you have to do it for just one set of flow rate, one set of operating conditions, namely wellhead pressure, tubing size, etc. But when you have a situation where you're trying to look over large number of wells and you're just in the greenfield type of development, then you have to conduct this type of exercise for wide range of scenarios, future conditions, and also you have to keep in mind the field constraints with the time. And this field constraints becomes more important not only in green, but also in the brown fields also. So one thing that helps a lot is that if you understand your production, injection gradients, and inflow performance relationship. And that should tell you that gas lift is all about understanding the hydraulics. Okay, you all, I'm assuming that are familiar with some gas lift. Otherwise, I can spend 5+ minutes just explaining this. But if I had to give you a quick summary of what this graph is saying, the thesis, what you're seeing on the right side here at the top is the gas lift well performance curve, which essentially gives you the relationship between the injection gas quantity and what is the liquid production rate. And as you might have guessed, with the increasing injection gas quantity, the liquid production rate keeps on increasing because your bottom hole flowing pressure is decreasing. But after a while, as we saw earlier, your bottom hole flowing pressure does not decrease, but in some cases it can even start increasing, and because of the friction effect, as I was explaining earlier. In that case, this curve may start going downward. Okay, so again, as a gas lift design or the operations engineer, your key uh, tool, if you will, is this gas lift performance curve, where you will see that, okay, how much am I going to inject in order to produce what? Now, we have to keep in mind that even though we talk in terms of performance curve, essentially we are dealing with a performance surface, meaning this curve needs to be prepared for multiple sets of conditions as your operating wellhead pressure changes, as your operating injection pressure changes, formation gas oil ratio changes, water cut changes, reservoir pressure changes, in case of greenfield development, diameter of tubing changes, etc., etc. So for each of these parameter change, you will have a different performance curve. And that's where when you assemble all of this performance curve, you come up with a hyperplane or hypersurface, if you will. And as an operating, when you are in the operations role, your job would be to navigate your injection gas quantity through in such a way that you get the maximum. And now there's one more thought I'm going to put here out, is that you have to keep in mind when you have multiple wells and you have limited injection gas quantity, then how do you distribute the gas? So far we talked about the gas lift design. Now, once you have operational gas lift in the field, then you have to think about the optimization. How do you maximize the available injection gas abilities to produce the most optimum rate? And that's where there is a five-step process here: system assessment, candidate selection, analysis, troubleshooting, intervention, evaluation. And by the way, again, we do not have time to talk about each of this in the class. We can go into more detail, but each of these, there are some related activities for each of these steps that needs to be understood in order to be an effective operations person. Okay. Continuous gas lift system, another thing to keep in mind is that it's a closed loop system, in the sense that in the normal well, you are connected, multiple wells are connected at the production manifold. But in case of gas lift wells, what happens is that you also have, you also have compressor station that is receiving gas from your separation system. Part of the gas might be going into the sales line. So all these wells are not only connected at the production manifold, but also at the injection manifold. And as I was mentioning earlier, when you have multiple wells with differing productivities uh, and differing characteristics, the challenge comes up when you have to allocate the right quantity of gas in order to maximize the production from the group of the wells. Um, So when you are in the operations, typically in the design phase, you look at the individual well, but in the operations phase, you have to look at also multiple well gas lift consideration. And as I have been mentioning, gas allocation can be a significant challenge because you have to keep in mind the pressure drops between wells, between manifold and separator, whereas the manifold pressure can impact the wellhead pressures. So we have to understand and know the gas allocation to calculate the pressure drop. But we also need to know the pressure drop to optimize the lift gas. So this becomes a very interesting optimization problem. And there are software available. And there will be some discussion in the class. Now, coming back to what I promised, that I'll point out what are the similarities and differences between Permian and Gulf of Mexico. So as most of you may know, Permian Basin is somewhere straddling the New Mexico and Texas on the west side of the Texas, nearby Lubbock Midland area, whereas Gulf of Mexico is south east of Houston or and south of Louisiana. So what you are looking at here, and why did I choose Permian and Gulf of Mexico and not Bakken and Gulf of Mexico or Eagle Ford and Gulf of Mexico? Because these are the two most prolific producing regions, as this number say here. From EIA DPR, we look at December 23, oil was almost 6 million barrels per day from Permian Basin. Gulf of Mexico was producing almost 2 million barrels according to 2023 November production numbers from Bureau of Energy Management. So these are the two most important regions, not only in the United States, but in the world. When you look at the production numbers, actually, if you compare these numbers to some of the OPEC nations numbers, you'll find that maybe three other nations would have higher numbers than Permian and Gulf of Mexico combined, or even Gulf of Mexico by itself is 2 million barrels is a high production. So these are not small basins. So the learnings that are being made here are very important. Again, this tells the same story. Now, one thing that is worth mentioning is that between 2014 and now, last 10 years, Permian Basin production has moved all the way from 1.7 to right now it stands around 6 million barrels. Gulf of Mexico is more or less flat. You can say 1.4 bumped up to 1.8 and now it is back to about 1.45 or so. Gas is a different story. Gas is 6 billion SCF gone up to 24 billion, whereas in Gulf of Mexico, gas production has declined from 3.5 billion to now it is about 2 billion. So this is a big macro comparison between Permian and Gulf of Mexico. By the way, this is the entire region production. By no means, and I do not have a numbers that what percentage is being produced using gas lift. But my assessment is that gas lift being the dominant method that it is, that percentage is fairly high. So it is worth considering what are the gas lift practices in this region. So now let's look at Permian and what is the gas lift practices that are relevant over here. Again, not all of the production coming from the Permian is gas lift driven, but you go and talk to anybody, gas lift is capturing significant amount of mind share from the operators. The thing about Permian, and again, we are going to focus on the unconventional because that is where all the production boost has been coming, as we saw from the numbers from 2014 and onwards. So what one thing we have to keep in mind is that this unconventional production, there is a steep ramp up and then there is a steep drop and then there is a long tail. So because of this production profile, we have to, whenever we are devising any lift method, we have to pay attention to it's what is called turn down ratio, meaning can that particular lift configuration hold? Can this lift configuration hold not only this higher rate, but also the lower rate, and how long it can hold so that you do not have to change out the equipment sooner, right? We have to consider what are the pressure maintenance requirement, lift system limitations, etc. Now, this is where gas lift really shines, and that's what operators are realizing. It was like earlier days, ESP was being utilized a lot in this area where the production were very high. But with the drop in the production rate, operators had to change out very quickly either to the lower size ESP or to switch over to another lift method. Gas lift, as we'll see very soon, allows them to move from this high rate, which could be as high as 5,000 plus barrel, down to almost 100 or even less barrels of production. Let's look at one case study from Shona Noonan's presentation in 2017. At that time, as this presentation, there's a longer version of this presentation, but why Oxy decided to go with the gas lift in Permian, where they tried with the ESP and rod pump is of course very well known and much practiced conventionally in the Permian. But they decided to go with the gas lift because this design is very tolerant of gas slugging. There may be multi-pointing. That is one of the challenge with the gas lift if when properly not designed or operated, but it is still lifting. Lifting range from less than 25 barrels to 4,000 barrels of fluid. You can redesign for production design without having to pull tubing. This is another benefit. No expensive lift conversions and not impacted by high dogleg severity. And another thing, this is very important, that there is a whole life cycle from cradle to grave that you can do with the gas lift, from annular to the conventional. When we say conventional gas lift, we mean production from the tubing. Annular meaning production from the annular space. Go to the intermittent, go to the gas-assisted plunger lift and chamber lift. As you will see later on, there are some intermediate steps like Pagel, plunger assisted gas lift, and so on. So operators are beginning to see the value in using gas lift because of this flexibility. So here is a slide that shows how you can look at the annular through tubing flow switchovers. And now some vendors are offering equipment whereby without pulling the equipment, you can basically switch from annular to tubing flow. And this, you are looking at the typical configuration that is deployed in Permian Basin, right? A takeaway is that when you are producing with the annular in the initial time, when your productivity is significantly high, you can produce as high as 3,000. And about this time frame, when your productivity drops, where the absolute open flow potential drops from slightly over 4,200 to 1,000 for this particular case, you can switch over to tubular flow because at this point, there'll be significant amount of liquid fallback. So you can have initial annular flow yielding about 2,900 barrels of fluid with the 2,000 psi. And once you reach about 1,200 psi of FBHP, then you convert over to the tubular. Another trend that is prevalent in, or that is increasing in not only Permian, but all the basins is downhole gauges, because that allows operators to effectively use. Here is an example from case study from the ConocoPhillips. They are not only using annular, but they are also using what is called high pressure gas lift. This high pressure gas lift basically allows you to have a single point of injection. The pressure is sufficiently high enough to be able to go significantly deep. And so when you combine that with the annular, as this operating envelope on the right side from ConocoPhillips shows, you can produce as high as 5,000 barrels of liquid, right? And what they are showing here is the operating envelope when they switch from annular flow to the tubular flow. Okay. The main takeaway is that because of this, they are not only able to reduce the compression costs, but they are also reducing early life lifting costs by almost $2 barrel of oil equivalent, right? Which can be significant when the pricing environment gets constrained, right? One more I mentioned about plunger assisted gas lift. This is inserting a plunger in the continuous gas lifted valves when the production rate falls below 500 barrels of liquid. Because of the fallback, due to the tubing size, the gas lift becomes less efficient. So you are inserting a plunger, a solid interface, to improve the lifting efficiency. So this is another, and this is a two-piece plunger or a bypass plunger. That is what is being used. And here you're looking at a picture courtesy of one of the service company, how operators are installing the lubricators and everything from the very beginning, so that when the time comes, you can just drop the plunger and you can convert a tubular flow gas lift to the plunger assisted gas lift. On the right side, you're seeing a picture courtesy of another service provider on how operators are using high pressure gas lift. So these are very, very high injection pressure, discharge pressure, compression setups. We are looking at close to 3000 psi discharge pressure, and in some cases even higher than that. Okay. Another experiment people are trying is not to use a traditional gas lift valve, but remotely operated gas lift valve. And then there are multiple approaches. One approach relies on adjustable orifices that can be opened and closed from the surface using the E-line. Another approach is, again, similarly using a valve that can be opened and closed from the uh, surface. Now, additional benefit of this remotely operated gas lift valve is that you also get a downhole measurement, because typically pressure and temperature sensors are incorporated into the electronics of this remotely operated gas lift valve. So this approach has very good potential, not only in Permian, but around the world. Okay, so the conclusion for the Permian gas lift is that most, if not all, operators are using gas lift. Many new approaches are being tried. I talked about single point or high pressure gas lift, surface operated gas lift valves, switching from annular to tubular to Pagel, etc. And that is what can provide cradle to grave solution. Conventional gas lift for medium to low production rate, and then you switch over to plunger assisted, and then intermittent gas lift in the lower production regime, and then you can go to chamber lift for extremely low rate. So with this, let's look at what is happening on the Gulf of Mexico side. What we are looking at here is a picture from the Bureau of Energy Management. These are the platforms, and these blue lines are the water depths from 200, 400, 800, and then I think this is 1600. The important statistics to note when you look at the production number for 2022 and even 2023 are no different, is that majority of the production is coming from depths more than 1,000 meters. So here you're looking at 46% of the production is coming from between 1,000 and 2,000 meter depth, and 35% of the production is coming between 2,000 and 3,000 meter depth. Even though we have so many installations and wells into the shallower, less than 200 meter, but the production coming from those platforms is less than 2%. I mean, less than 8% collectively when you go up to 500 meter water depths. So majority of the production is coming from the deep water, and gas-rich artificial lift is popular in the deep water. And here is another graphic that shows in the deep water what is the percentage. And here the deep water, for the purpose of this graphic, is defined as the water depth more than 1,000 feet, or roughly about 300 meters or so. And what we are seeing is that over the years, beginning 2000 or so, deep water production is consistently increasing. It was about roughly about half in 2000, 2001, and now it is approaching more than 90%. Now, with the deep water production, we have to also pay attention to what type of production systems. In shallow water production, you have typically fixed platform, whereas as you go deeper, you have spars or TLPs or tension leg platforms or spars, or you can have FPSOs or the floating production storage and offloading system. And what we are finding here, I'm showing one example from the Shell, Shell has maximum number of deep water development in Gulf of Mexico. PowerNap and Vito are two recent development. And what you're looking at is this part of the Gulf of Mexico where this PowerNap and Vito host are located. Okay, what this says is that PowerNap is a subsea tie back to the Olympus tension leg platform with three production wells producing through single insulated 19-mile flow line and high pressure gas lift capability. Okay, here coming to Vito, it has 8 subsea wells, 9,400 meter or 31,000 feet with almost 5,500 meter depth, right? In well gas lift and associated subsea. Okay, and I can go through a few other developments like this, though I do not have exact number of gas lifted production, but based on the announcement that I have seen, it is safe to say that gas lift is producing majority of the production. Here, I am showing this subsea development schematic just to point out few things. Of course, you have your tension leg platform or FPSO, and then there are subsea wells that are connected through some sort of umbilicals or risers, right? And the same situation is with whether there is a spar type of system. So with that in mind, let's go back to one presentation from Shell in 2019, where they laid out why they wanted to have a very rigorous gas lift validation, right? Because this project is only economical with gas lift. Look at the cost, 75 to 100 million just to drill and complete a subsea well. If you have to pull a subsea tubing, it costs 20 million. If you have to recomplete upper completion, 25 million. So they rely on gas lift because you do not have a need to pull as much. It makes the project economical, okay? And intervention cost for artificial lift system is substantial. So they are looking at increased reliability and run life, okay? Decrease intervention frequency. And that's why gas lift shines, and that's why it is preferred in deep water. However, the traditional equipment would not work. And why? Look at here, subsea well here. If it is 4,000 feet water, bottom hole pressure, you're looking at 23,000 KSI, bottom hole temperature 350 Fahrenheit, right? They look at 30-year well life. So with that in mind, now let's go back onto the vendor side. Vendors who are being asked to provide this system that can handle subsea gas lift, they have to look at increased pressure temperature rating, metallurgies are different, they require special features, bypass slots for cables. Remember, there are some measurement devices that are being lowered inside. And then there is a barrier technology with your pockets. So if you look at, and by the way, I'm giving this here at the bottom, the sources where from I'm taking this. So they have to conduct a significant amount of finite element modeling of what one would consider a traditional side pocket mineral. They have to look at some of the materials, and those are expensive material because they need to be high strength with the yield strength exceeding 100 KSI, okay, meaning the production costs are higher, okay, plus because of some points where there is a high stress is experienced, they have to also pay attention to their machining and assembly processes, welding and heat treatment processes, and whole API standard has been developed. And in the previous slide, as we saw, Shell even said that they need to have their own playbook in order to develop this deep water gas lift resources, right? So another thing we have to keep in mind is that there is also riser-based gas lift that is deployed in deep water subsea systems. And if you want to learn more about it, there is a very nice OTC paper almost 15 plus years ago that was published from Shell. Okay, so there are three ways gas lift can be used: production enhancement, flow stabilization, flow line depressurization. So you have to look at the system flexibility and riser insulation. And why I'm bringing up all of this is that when you go into the deep water gas lift, you have to not only pay attention to the traditional gas lift related hydraulics, but you have to also pay attention to other issues, flow assurance issues, uh, particularly when you are depressurizing. What happens when you have liquid into the line and all of a sudden uh, when you are in a specific pressure and temperature area where the hydrates are likely to form. And if you do not know, hydrates can plug your flow lines and can disrupt the production. So some of these considerations, which you will not see when you're working in Permian, are of paramount importance in deep water Gulf of Mexico type of development. And as a result of that, typically when you're developing gas lift or the entire project can multiple years of effort. Um, like the Permian type of gas lift where it can be done in less than a month or so. So in conclusion, gas lift typically reduces the fluid density and helps fluid rise to the surface with available reservoir energy. It's a versatile lift method used very widely in Permian as well as Gulf of Mexico. Permian application can range from 3 to 4,000 to less than 10 barrels per day, though there are higher number of wells. It's typically application is driven by the steep production rate changes, meaning you have to think of how gas lift can provide cradle to grave solution from annular to tubular to pagal to intermittent plunger, gap valve and chamber lift. Innovative approaches, I mentioned two. There are many other things that have been tried also. There are some flow assurance issues in Permian also, which I have not covered here, but we can talk in the class. But here we talked about single point gas lift, pagal, and remotely operated gas lift. Coming to Gulf of Mexico, we have production rates from 5,000 in deep water to less than 100 barrels. Actually, some wells have more than 5,000 barrels of liquid as I was examining some of the production rate data. It's a typically deep water application, even though in Gulf of Mexico, we also have shallow water application. There are many, many wells on gas lift in shallow waters as well. And in many ways, it is not much different from the onshore application, though it has some specifics that needs to be paid attention to. But deep water is where uh, there are some issues related to not only higher pressure and temperature, but also flow assurance. So there are some special gas lift valve mandrels that can meet the barrier specifications, that can meet the longevity requirement, have been developed. Um, and I believe with this, um, I come to the last slide and we are open for question and answer. Susan.
Thank you.
Thank you.
I want to remind the audience that you will receive a link to the recording of today's webinar later today, an evaluation form, and a link to about the training course that Dr. Shoshi is teaching on producing unconventional with gas lift from annular to pagal to plunger lift and in between, which will be offered in SCA's Houston Training Center on March 4th through 6th. Can you talk a little bit more about the flow assurance challenges? You mentioned hydrates in the Gulf. What might be the challenges you could encounter with flow assurance in the Permian and with gas
So
lift?
yes, so in Permian, one challenge that I have heard from operators about is the paraffin or wax deposition. So as the injection gas expands and there is some cooling going on, so typically operators are looking at what to do about the paraffin deposition. Of course, you can go for the hot oiling, but that means disruption of the production. So there are some approaches that people have tried to alleviate this challenge. Particularly, what we are trying to do is maybe change the cooling process when the gas comes out of the compressor, try to not cool it down. So hotter injection gas can take care of some of those paraffin. So that is one challenge that I have seen. Another challenge could be sand and the proppant that comes back. Good news is that the gas lift is not impaired. The lifting abilities is not impaired. However, from the facility side, you still have to have some of the considerations like erosion related issues that you have to pay attention to, and also once all of that sand comes to the surface, how to handle it without your systems getting plugged or you're separate. So those are the two things that come to my mind.
So I think gas lift is traditionally used in the co for one reason because of deck space for lack of space for other types of artificial lift. Can you talk about the economics of using gas lift if you have, for instance, an unconventional reservoir in the Gulf of Mexico? Would that work?
Wait, I did not
Eh,
catch the
I'll,
last
I'll,
part of
I'll
it.
say it again. Are non-conventional reservoirs in deep water economically viable with gas lift?
Correct. I'm pretty sure as long the gas lift has been considered fairly viable in most of the areas. The main challenge for the gas lift comes if you do not have sufficient gas, right?
Hmm.
And I have seen that challenge in some of the North Sea cases, like where as the water cut keeps on increasing, uh, you do not have sufficient gas because you already have made a sales commitment. Now, you may argue with me that this is a closed loop system, so the gas is not going to go away, but there's always some gas losses. So, where I'm going with this is that you have to project the injection lift gas requirement beyond the current conditions and then make appropriate adjustment, because what happens, especially if you have strong water drive aquifer, then your formation gas quantity may go down, and in that case you may not have sufficient gas to meet your injection gas requirement as well as your sales requirement. So as I was mentioning, I have seen some cases whereby operator had to actually buy back some of the sales gas in order to inject it. Hope that answers the question.
Thank you. Yes. In slide 17, I think you showed some of the uh, projection production for both the Gulf of Mexico and for the Permian Basin. And is there a concern with the declining Gulf of Mexico regional gas production that that gas may not be available in the future for gas lift?
That is definitely the thought I had when I was preparing this slide, when I looked at the direction in which the regional gas production is going. Now, keep in mind that this is the entire Gulf of Mexico region. I would have loved to separate out the production data whereby I can see that what is the situation in deep water. Are we seeing similar trend over there or not? And maybe I'll do that at some point, but right now I do not have answer. So yes, looking at this, one can say that, okay, for 1.5 million and we have 3.5 billion cubic foot. And when you go for 1.4 million, which is prime predominantly, as we saw, almost 80% is coming from deep water. And then the gas is less than maybe not quite half, almost one half of what it was before. So there would be one consideration. Now, however, keep in mind that some of these deep water reservoirs have very high energy, meaning high pressure reservoirs, right? So oftentimes your gas lift is, your injection gas requirements are not as high. You will need gas lift primarily for production enhancement and for other things that I mentioned in the slide, like blowdown and such. So the injection gas, but however, I do not have exact numbers. That would be a very good exercise to perform that. Okay, let's look at the deep water production data. What is the injection gas requirement? But that is for the training class.
And conversely, I might ask a similar question with the increasing gas production in the Permian region. Is gas lift an opportunity to use some of that gas that may be um, uh, not able to put into the pipeline or perhaps being flared for lack of pipeline capacity? Is that the reason why you think gas
You are
lift is being used?
You're so right that gas lift can help with some of the quantity of this gas. However, we have to keep in mind that it's a basically recirculating gas, meaning your offtake for the gas lift will not be as high. And one of the reasons why gas lift has taken off in Permian is primarily for that, because we have so much of gas and not sufficient pipeline capacity to take it away. And then with the IRA implementation this year, there is a significant pressure on the operators to cut down on the flaring, right? Because of the methane and CO2 related emissions. So gas lift really provides a good. Now, some of the operators, and again, I'm going too much into weeds here, but they are going into centralized compression facility, and they are basically removing pad-based separation altogether so that they can handle the gas much better and take care of their environmental obligation, ESG obligations at the same time.
Very good. And talk about the hybrid gas lift option moving from the annular to the tubular over the life of the well. Is that more expensive to set that up, or how does that work?
Okay, so this is a valid consideration that annular to tubular would be more expensive. Actually, not. Earlier, people used to say that when you do annular flow, then your casing integrity is compromised, etc. But you have to keep in mind, we are in unconventional territory where casing is as such subjected to very high pressure fracturing fluids. And as against that, the production using the gas lift does not apply that much higher pressure. So that part is already covered. Going back to the cost question, uh, the main cost would be if you have to pull out, because earlier it used to be the case whereby you can have annular flow, one type of coating on the mandrel, tubular flow, another type of coating on the mandrel. But now some of the vendors are providing the ability whereby without pulling, meaning taking care of that, without pulling the tubing, you can basically switch over from annular to tubular. So the cost part, when you compare the cost of compare it with the ESP, is not as significant. Most of the cost on the gas lift is on the compression side, which is on the surface, right? But not
So
into
you
the
might have to have
wellbore.
those remotely operated valves to be able to do that operation.
So remotely operated valve, now that would be more expensive operation compared to the traditional gas lift, right? But there, what operators are looking for is a better control on the injection point and injection quantity. In order to make the gas lift work, you have to have a you have to remove multi-pointing and you have to inject at the right location. Now, with the changes, what we are looking at here, this productivity IPR versus this IPR, your injection point has to be significantly different, right? With the lower pressure, your injection point moves deeper. Now, at that time, if you have to pull the valves, now some people may not use side pocket mandrel, they are using conventional mandrel. In that case, they will have to pull the entire tubing. So using those remotely operated valve, one of the promise of those is that you can activate and deactivate the valves at particular depth depending upon your valve's productivity. Plus, you have downhole data coming in from the associated pressure temperature gauges, but it doesn't make them cheaper though. Okay?
Very good. Well, we've reached the end of our hour today, so I want to remind our listeners you'll receive a link to the recording of today's webinar, an evaluation form, a link to SCA's website with more information about the training class on producing unconventional with gas lift from to Paggle to plunger lift and in between, which will be offered in SCA's Houston Training Center on March 4 through 6. Thank you very much. Goodbye.
Thank you. Goodbye.